There we go. Hello. So today, like I just said before I unpause the recording, we are probably going to have a relatively short session, which is mostly due to the nature of what we're talking about today, which is confounds. Creatively titled The Haunted Dag and the Causal Terror in the book by Richard McElraith. Just to get right into this, I feel as though I should mention Richard's work on categorical variables, not necessarily his work, but his input. Part of this was covered in the last lecture, part of this was covered in this lecture. Because last lecture was quite a bit of material, I chose to put it in this one. So basically, these categorical variables and the explanation pertaining to them all comes down to how we think about them and how we implement them into our models, or statistical golems, as McElraith would have us say. So there are two distinctions here. One is indicator variables, one is index variables. Indicator variables, like the name would suggest, indicate whether something is the case or not. So they are binary in nature, 0 or 1. And they tell you whether an observation belongs to a category, then usually it takes the numeric value of 1, or not, then it usually takes the numeric value of 0. So if you have a variable that you call male, for example, a 1 would identify a man and a 0 would identify a woman. Now, if you were to call that variable female, then the 1 would identify a woman and the 0 would identify a man. That's just so that it's much easier for people to read and for you to revisit some projects, or even the same project that you're already working on, but now you just want to put a variable in that you were recording when you did the data recording, but you didn't quite keep good track of what you made your 1 and your 0. Always make the 1 the affirmation of the title of your variable and the 0 the negation of it. But that's only if you use indicator variables, which there are a lot of cases for why you shouldn't. What this does, in fact, when we go into the actual maths behind this, is that it turns a parameter on and off. So as you can see here in this example of this linear equation here, you can see that when beta m, so that is someone male or not, if this is set to 0, so we would have a woman, then we would obtain only alpha. Because whatever m tells us, and I think m is mass, h is height. So this is height as a product of mass with a parameter dependent on your sex. So you only really estimate the means for males and females. The male height would be given by alpha and beta m, whereas the female height would be given only by alpha, because beta m would be 0 in that case. Now this brings with it a few problems. The first one that should initially come to mind is that we set a prior for our beta m, and this means that for our female observations, where we only look at one parameter by itself, alpha, we only have the uncertainty that comes from that. So that's the only source of uncertainty for our predictions of height of females. However, once we have a male, we suddenly have two parameters that need to be estimated, alpha and beta, and that suddenly doubles our sources of uncertainty in number, not necessarily in our uncertainty itself. That doesn't necessarily double just because the number of parameters that give us uncertainty doubles, but we do have more sources of uncertainty, which automatically makes our model biased against a certain indicator of category. Another problem with this is the dimensionality, because for a number of k categories, you need k minus 1 indicator variables. So in the example of seasons right here, which I found to be quite illustrative of this, you can see that if you have 4 seasons, for example, you only need 3 indicator variables, because a 0 in the 3 already implies a 1 in the 4th. And here we go again to picking our priors for the indicator variables. This can be very tricky because you might like to assign the same prior for all of these. And then that just becomes a writing exercise that can be a bit tedious. But the more subversive problem that might stem from this is that of what I just mentioned, you have multiple sources of uncertainty suddenly, and then tracking that uncertainty along might really bias your results. Moving on to the preferred solution by Richard, and I have to say this does look a lot better to me as well. These are index variables, and I'm sure we have all used indicator variables or index variables at this point in our models at some point, so I'm just going to rush through this a bit so we get to the actual confounds of today. In theory, index variables are usually nominal or ordinal, so that is 1, 2, 3, 4, 5. You usually can't do math with them. I don't see why you couldn't. In the book and the lecture itself, Meg Elreath always mentioned that these are unordered, implying a nominal scale instead of an ordinal one. However, I don't see why you shouldn't be able to code small, medium, big as 1, 2, 3, which are orderable and should still work the exact same way as if it's just colors, for example, which you can't order, but you can code as numbers. So that's why I would say these can be nominal or ordinal scale. And of course, because a special case of the nominal scale is the binary scale, they can also be binary. So you can still describe male and female with this. You would just usually not write 0 and 1, but 1 and 2. So the prior is always active instead of having uneven numbers of uncertainty sources for different categories. This keeps your model specification constant, meaning you don't have to add another prior for another category, which you would have to do if you had a beta winter, beta summer, beta spring, and beta fall, for example. This keeps it all the same way. So you can plug multiple different data sets in terms of how many categories are in your index variable into the same model specification without needing to alter that specification by itself. And also this, at least it said so in the lecture, is the foundation for multi-level models. And I am just waiting for us to get into multi-level models. I'm really excited for those personally. So for K categories, you only need one index variable, as long as all of these categories fall into the same realm of interest. So for example, I would not record in the same index variable seasons and, let's say, regions, for example. I would have an index variable for seasons and an index variable for regions. However, irrespective of how many regions I identify, I only ever need one index variable because I can just populate it with as many values as I have regions because I'm not bound to that binary underlying problem. So one way to do this, to stick with the sex example, is with your binary index variable, and I need to change this up here. It should say 1 to 2. I just copy pasted because I was a bit lazy on this. So this up here in the theory section should say 1 to 2. As you can see down here in the R section, now we transfer all of our male and female data to 1 and 2 so that the beta parameter is always turned on and we have the same amount of uncertainty sources. Now we can assign the same prior to each category relatively easy. And in our code, what we can do is just identify a different alpha for every sex. Sex is one of our variables in the data set, as you can see here, coded as 2s and 1s. And we can then just set the same normal distribution prior for all of these alphas into sets that are driven and distinguished by the different sexes. And if I'm not making sense anymore, just stop me and we'll talk about it right away, because if everything's fine so far, we are going to get into the actual meat of what this lecture was about. And right up front, I have to say this had me majorly excited because everything was graphs, and I love graphs. And I know you know that I love graphs, but I still feel like I have to say it because I just love them so much. So what we talk about today, for the most part, is all around confounds. Which variables to include, which variables to not include in a model based on causal patterns that we infer or hypothesize and put into directed acyclic graphs. So the first one of these is a fork. In theory, this often coincides with multicollinearity because of an association between two variables via another variable which is associated with both of them. So in frequentist analyses, we often call this multicollinearity. In terms of this, and I have shamelessly stolen quite a few of the lecture slides here because why should I type this out again when it's already done quite well? I could have typed this out just to get rid of that somewhat ugly font that was used in the lectures, but I didn't feel like it. So now we have to stick with this pen kind of font on here. At least it's not Comic Sans, guys. So what we have with this DAG here, the fork is driven in such a way that Z is a common cause of X and Y. It's called a fork. It's called a fork because I guess at some point people had forks with only two tongues, and that's it. And if we look at this, we can see that X and Y are independent of one another. However, X is dependent on Z and Y is dependent on Z, meaning as soon as we account for Z and we know X, there's nothing more to be known about Y that we don't know from these two already, and vice versa. Which then brings us into this mathematical notation and deconfounding. So this is called a confound because of Z being a common cause of X and Y. We can deconfound this by conditioning on Z, which then removes the dependency between X and Y, which is put in place by both of them being a product of Z. In mathematical notation, we can say that X is conditionally independent of Y given Z, meaning X is independent of Y once we account for Z. And that's the whole shebang behind forks. And while I was reading up on this a tiny bit more, I read, and hope it's true, I got it off of Wikipedia, so I'm a bit hesitant about it. And you can see my high school education about Wikipedia being an inherently untrustworthy source still lying deep within me there. From what I understand, this is reversible. So this notation can both mean X is independent of Y conditional on Z, but also at the same time, without needing to write it out, Y is conditionally independent of X given Z. And to me, that makes sense. So I would acknowledge this as the truth. But if someone of you knows something to the contrary, then let me know, or let us know. Otherwise, I'm just going to assume that these are reversible. So to go with an example for this, because that's always easiest, at least for me, to learn new concepts. This is basically the divorce example that we were talking about last week. So where we looked at the Waffle House data set, and we looked at marriage rate, marriage age as predictors of the divorce rate. And the fork in this case is that age both drives marriage rate, because you have more time that you're alive, you have a higher chance to find someone you feel like marrying, or your chances of your parents pressuring you into a rise because of your rising age might be another factor there. But also, the older you get, the more tired you might become of your partner, and you might want to have a divorce. And I know that sounds very bleak. I'm not an expert on this, so don't quote me on any of this. But that is the fork that we get from this. So once we look at the association between marriage rate and divorce rate, we find a correlation between the two. And without knowing of the underlying causal inferences here, or the DAG, we could assume that marriage rate drives divorce rate, which would make sense because you need to be married to actually be able to divorce. However, once we account for age in this, suddenly marriage rate is not important in identifying divorce rate anymore, because all of the information is gobbled up by age, which is where it stems from. So next confounder, after just having dealt with the fork, is the pipe. In the pipe, information flows from one predictor to one response via a number of intermediate nodes. In this case, just one, because that's easier to look at. So in this case, X begets Z begets Y. So what Z does is it mediates the association between X and Y, and it picks up on, so if we were to try to understand what's happening here, what Z or what Z does is that it takes up all of the information that is already passed along between X and Z. So let's say these are highly correlated and X has a really strong correlation with Z. If we just plug all of it into one model, the model will only pick up on Z because that is lying closer to Y and contains almost all of the information that X could ever give us. So what we could do here would be to condition on Z, which would actually give us a confound because it removes this dependency that we want to see between X and Y. So this is also known as the, and I know I'm not using my words quite well right now, this is known as a post-treatment bias, where we would be interested in, and I'm just going to go with the lecture example here, we could be interested in a antifungal treatment X, which gives us a certain output of fungus infestation in the soil, and Y would be our growth rate or vegetative height of plants in these treatment plots. Now, if we were to just plug all of these variables into one model where we try to predict Y as a function or a linear combination of X and Z, then only Z will come out as very informative. Because as a matter of fact, it's the fungus that drives vegetation height. However, the fungus itself is influenced by what kind of treatment we used. And the treatment could be a really good example of an index variable because we might have more than just 2 treatments. What we are interested in, however, is to identify the effect of X on Y. And if we have Z in our model, so we condition on Z, then suddenly Y becomes conditionally independent of X, which would lead us to not identifying the treatment effect that is actually there and which we were after. So as an example, and I totally forgot I put that in here, is the fungus example that I just talked through. And in DAG speak, and I was really happy that someone finally explained this to me in a way that I could understand properly, because I usually don't get the super complex formulae that people in graph theory like to use. When we talk of conditional independence in pipes, we also, in DAG speak, call this D separation, D standing for directional. And what that means in this case is that when we look at treatment, 2 fungus, 2 H1, which is the height, our outcome, we can say that F D separates, so directionally separates H1 from T. Hope that makes sense. Now, when looking at this, at least that was one of my initial thoughts, because I work with somewhat complex DAGs, and I'm just now learning to break them down and then build them up piece by piece. I should have done that way earlier, but at least I'm doing it now. In these kinds of experimental manipulation studies or simulation studies, it's relatively easy to find these DAGs and to make good assumptions of where you should look for your conditional independence or your D-separation and how you should then condition your models. Now, the problem is that once you go to observational studies, which is what we almost exclusively do in many biological subfields, we do not know the underlying causal network. So identifying where the information flows, so to say, along these directional edges is somewhat difficult and absolutely non-trivial. So controlling for every available variable is then likely to block some pipes in some places where you don't want them to be blocked. And you need to do variable selection, which I hope we'll get to hear a bit more about, even outside of the realm of DAGs, because as much as I like them, I can foresee quite a lot of situations for any one of us where drawing a DAG will be nigh impossible with the kind of study settings that we're looking at. So to sum up, if we condition on a node, that then blocks all of the nodes on the same path that are further away from the outcome that we're interested in. Because now we are just looking at all of the information that is stored within that one node that is closest to our outcome on this one path. Next confound is the collider, which is the inverse of the fork, where x and y jointly cause z. In this case, x and y are truly independent. However, when we condition on z, we create a dependency between x and y, which is purely statistical, but not causal. Because now when we know what x is and we learn what z is, we can infer what the y value is. And I actually loved the example from the lecture on this one, where we can learn about one side of a diag by knowing the other side and the central node. So in the example of light being a product of whether electricity is present and a switch has been flipped to the on position, if we know that the light is off and the switch is flipped to the on position, we are quite sure that the electricity has gone missing. So just intuitively, I'm sure that every one of us has at least at some point experienced a power outage. And that is one of the first things we do. We go to a light switch and we flip it back and forth like madmen, thus inferring about whether electricity is present or not. And then usually grabbing the nearest candle or torch or telephone. And this works in both directions. So if let's say we have an actual fork handy, and I don't recommend doing this, neither at home nor anywhere, and next to our light switch, there's a socket. And we flip the switch back and forth and it doesn't turn on. So now we just jam our fork into the socket and the obvious happens. Then we know that the switch is probably in the off position if we get electrocuted and the light isn't on. Now that's an easy example for this. However, there are more complex ones. And the one that came up in the lecture, which actually took me a tiny bit of time to comprehend, is whether older people are less happy and how we could control for marriage status. This all goes off of this tag down here, where we make some assertion that age has a positive effect on marriage, because the older you get, the more people you will have met that you might want to possibly marry, and they might be in the mood to marry as well. So that drives your marriage rate higher. Happiness makes you want to marry faster, because you have a good outlook on life, whatever, not a socialist. Sorry, social scientist. Oh God, I'm sorry. I grew up in the remnants of East Germany. I can call myself a socialist, I feel like. Irrespective of that, we might also want to hypothesize about what age might do to happiness. Do you get happier the older you get? Do you get sadder the older you get? Well, in this simulation of data that you can see on the right-hand side, there is no effect between these two. However, if you just look at what happens within these groups of married or unmarried people, over time they get less happy. And that isn't because there's a negative effect between age and happiness, because in the simulation there definitely isn't. It just comes down to the groupings in your data. Because as you get older, you are more likely to marry, and the more happy you are, the earlier you marry. Because age doesn't have to have a strong effect on your marriage anymore. So you can see that the first individuals that get married are disproportionately happier than the rest of the population. However, as the population gets older, the not so happy people also find partners who are probably equally as unhappy, which paints a grim picture, but leads to the effect that now there are more unhappy people in the married group, and the people in the unmarried group are on average even less happy than they were at the beginning of life. And that's where we get that kind of collider, because on marriage, we have the collision of age and happiness with a backdoor pathway, which we'll get into in just a second, of age to happiness to marriage. So an indirect effect. Now, another example for this, which I didn't want to omit because I found it quite interesting, and again, it took me a bit of time to get my head around, is all about unmeasured variables, because we will, by definition, always have unmeasured variables in any of our experiments, setups, observational studies, what have you. And if you have to go down to quantum theory, there's always going to be something that's unmeasured. So including unmeasured variables isn't a bad idea. I'm not suggesting you should down to the atomic level to find some unmeasured variables, because at that point you have probably carried it a bit too far. But at least for my work, I always have to deal with unmeasured variables. So in this example, we look at the influence of grandparents, the G's, and parents, P, on the education of their grandchildren, C. However, there is an unobserved variable, which in this case is neighborhood quality. So upscale neighborhood, the slums, what have you. And this introduces a collider on the parent node, because now we have information coming in from the educational background of the grandparents, as well as of the environment that the parents themselves live in. And this unobserved variable of the environment also has an influence of the grandchildren's education. So down here is a bit of R code of how to simulate this. I'm not going to go in depth on this too much. By the way, once I'm talking about R code, I found all of the code from the book in plain text format on the internet, because I'm sure many of you may have noticed that copy pasting it over from the PDF is a bit worrisome, because you have to do the line breaks manually. I have found a TXT file which has all of the different code chunks in it numbered correctly, and I uploaded that to the literature folder of our Mega Drive, so all of you have access to that as well. I also found a solutions handbook to the print version of the book, which is also in there, and that solutions book was authored by Richard McElraith himself, so that's on there as well now.
Hello? Hello, Eric.
Hey.
Yeah, so I have a question. Sorry to bug in. So if you go back to the previous example where you were talking about age, happy, and marry. So can we think of anything that could be like a collider or like the other example? So can we say maybe region can also serve as something that affects, like an unmeasured variable that affects what we are having here?
Absolutely. I would argue, and everyone else, feel free to step in at any point. Thank you for asking your question right away, everyone. I would argue that the region or environment quality that you're in should definitely drive how happy you are, and potentially also drive how likely it is that you marry. Because if you live in a highly urban area, you might not fancy getting married because there's no good place to marry if you want to have those nice Instagrammable pictures with your newlywed. However, if you live in the countryside, you might be happier, because we all know that the countryside is just far superior to the city. Fight me. And you also will most likely be more ready to marry because there's a nice backdrop to it. And because that's what you do in rural areas, right? Everyone gets married. So I would argue that could be an unmeasured effect that we could have in here. In this simulation that you're seeing the data points of on the right-hand side, that's not the case, because that's not how the simulation was set up. But if this were real-world data, we would definitely want to account for the region where those data points came from. Did that sufficiently address your question?
Yes, it does. Thank you.
Cool. All right, back to this one, and staying with environmental goodness or quality. So once we condition on the parents, because the parents are now a collider, once we have this unobserved variable in here, this opens up a backdoor. So this opens the path from G through P through U, which we haven't measured, all the way to C. And that can then significantly bias our results and lead to the fact that we can see a negative relationships between grandparent educational status and grandchild educational status. And just intuitively, this is certainly not going to be the case, because I would be highly surprised to meet any grandparent who, maybe a deacon at a university, goes up to their grandchildren and says, do not do anything that has a career path with education associated with it, because it's a waste of your time and your life. I don't see that happening. However, that's with intuition that we have of these pretty easy examples. In biological settings, that might not be quite as easy. So we could have identified that something's going wrong here just because of intuition telling us that a negative effect of grandparent educational status on grandchild educational status probably isn't a thing. And we may have to redo our model somehow. Now, once we go to actual big stuff data biology, where we can't just look at numbers and see whether something is accurate or not, or likely or not, we might want to draw up some DAGs and add on some unmeasured variables that we know are there, but we just don't have data for them, to then identify what we have to condition on and what we don't have to condition on. And also a side note here, whenever the book, Richard, or I say we condition on a certain variable, condition on just means we include it in the model. I probably should have said that earlier. So if we just plot this, and again, we see that there's a certain selection bias here. So when we look at all of this without neighborhood information, we would find this negative relationship. However, there's a certain trade-off here. You can be in a bad neighborhood and have a highly educated grandchild, but then it takes a highly educated grandparent, for example, because a highly educated grandparent will in turn spawn a pretty educated parent, which then has a positive effect on the education status of the child itself. And for that effect to take roots in a bad neighborhood, you have to be much higher educated than you have to be in a good neighborhood. And that's how that unmeasured variable really confounds what it is we're looking for. So again, we need to identify which backdoors to shut, what even are backdoors, and how to move on from there in variable selection. And I hope that one of our, actually the next input speaker on the 12th of February, Florian Hartig, whiz kid, not quite kid, but a wizard, will be talking about model checks and variable selection. And I hope there will be more on this kind of stuff, because I would like much more information on this. So this all brings us to the backdoor criterion, however. Confounding, which is a bad thing for us, is caused by the existence of open backdoor paths, as they are called. We need to shut all of these backdoors or paths that lead to our response variable. So in this case, E leading to W is the direct path we're interested in, with a backdoor going from E to U to W. These backdoor paths can go in directions that are not indicated by the edges themselves. So by just looking at this, you might say, well, there is just one path between E and W, because this arrow from U to E just flows in one direction. That's causality. Information still flows in both directions. So this path is still open. The only exception to this is the collider, which is a shut path by definition. So if we block all confounding paths between a predictor and the response we're interested in, so in this case, the path EUW needs to be blocked or shut in terms of backdoor terminology, we can then make some good inferences of the actual causal relationship between E and W, our predictor and our response. So knowing the directed acyclic graph, the DAG, we can shut and open paths or doors as we please. However, this gets out of hand super quick, and luckily there's a set of rules to deal with this, and R can handle most of this for you as well. So in terms of rules, I just wanted to take us back to this overview slide here for the different confounds that are potentially present. With the fork, what we would want to do is we want to condition on Z to shut the path between X and Y. If we, with the pipe, condition on Z, we would shut the path between X and Y as well. So the fork and the pipe are equivalent in the sense of how you would shut paths. With the collider, we already have a closed connection unless we condition on Z. Then we open the path, because then we introduce a relationship between X and Y on either end. Now the descendant we haven't talked about, and that's because it's basically a pipe with a weak connection in the middle. So if we condition on A, we weakly shut the path between X and Y because A has some of the information that's in Z. So we shut the door halfway, let's say. It's still better than nothing if we just can't measure Z, but we know that A is the descendant of it. We would probably, preferably, like to shut the pipe via Z, but if we don't have data for it, that's my understanding at least, then we would condition on A. So in summary, to address confounds, what we would like to do is we want to list all of the paths connecting our potential cause of interest X with the outcome Y. We would then classify each path by whether it's open or closed, and a path is open unless it contains a collider, or we condition on the variables therein. We would then have to classify each path by whether it is a backdoor path. So backdoor path has an arrow that is entering X. And if there are any backdoor paths that are open, we would then need to decide which variables we have to condition on to close these backdoor paths. Our indirect effects, so an outgoing arrow out of X that somehow via other nodes leads into Y, we wouldn't want to shut because that's valid information, because we want to know about the direct effect and the indirect effect. Unless we are in a study setting where we don't want that, then we would want to shut that path. But usually we're interested in the total effect of X on Y, so we would also want to account for the indirect paths. But backdoors need to be shut. And with that, I have reached the end of this summary. And if there's more input from you guys, I'd gladly hear it. Otherwise, I would transition us into the practical exercises for the day. That does not seem like anyone has the urgent need to say something.
A quick thing regarding the very first point of these index variables versus the other ones. I think the problem in doing math with this is you have like this beta times 0 variable, and by having 0 and 1s, you once turn it off and on. But if it range from 1 to 6, the number 6 in your unordered ones is like 6 times your same prior than the 1, even if they are not actually being able to order it. You know what I mean?
Yes, I see what you mean. Yes, so you don't, correct me if I misunderstood. I'm just trying to put it into my words. With the parameter estimates that we get in the end, we wouldn't want to do maths where we would, for example, say that beta 1 has to be exactly half of beta 2.
Mm-hmm.
I think that's what you're saying. So what I wanted to get across when I talked about nominal and ordinal distributions there is that ordinal just means you can order them, but not necessarily do math with them, right? So small is smaller than medium, and medium is smaller than big, but small plus medium does not equal big.
Yeah.
I took a bit of issue with McElreath's wording of they have to be unordered, but that might also just be reliant on how I was taught statistics and how I teach statistics, because for me, ordering does not imply that you can do math with them. It just means greater or smaller. But that might be pure terminology. Do you think we're on the same page, Bernd?
I think at least roughly. Like I'm wondering how it's influencing then in the model. For example, if we have like 6 unordered states, then like depending on which number you assign to which state, like for example, America becomes 6 times more democratic than Germany if Germany is 1 and America is 6, or you put like Sweden somewhere on the 3 or whatsoever.
I don't think that should have any effect, to be honest. Because you would still look at all of these estimates in isolation, wouldn't you? I don't think that ordering would change anything. As long as you still treat them as categories, so as distinct categories that you can't do math with. So because 2 times Germany does not equal 1 USA, for example, you would still be well within your rights to order them with any way you want. And if you want to order them, let's say you want to order them by their population size, for example, you could do that, but that's just semantics of which number do you assign to which country, because the model can only handle numbers instead of character strings.
Yeah.
Cool. In that case, I'm transferring us to the practical exercises. And I have noticed that the PDF version that's freely available on the internet probably has far, far less in terms of practical exercises than the print version has, because the PDF version doesn't even have easy exercises. Gregor, did you manage to get through the print exercises this week?
In fact, I did not. Unfortunately, I didn't have time yet.
That's all right. In that case, so who of us managed to get through either the print or the PDF exercises? All right, oh, Bernd, you as well.
Yeah, I did the print ones from easy to medium and stopped after reading the first sentence of the first hard one.
Cool. In that case, I'll probably hand this over to you to cover the easy exercises, because I'm sure they will still be useful if we talk about them, because these easy ones are usually, by nature of being easy to digest and explain. And then we can share some of the medium stuff, and I'll take over with the 2 hard exercises that were in the PDF version. Sound good to everyone? Cool. Bernd, do you have it written out somewhere, or should I just...
I've written out in a very ugly markdown script. I'm looking for the share button. Yeah, and I found out that I only did 2 out of the 4, but you will see, like, the first easy question is it's not nicely set up and everything. So the first question is like, list 3 mechanisms by which multiple regression can produce false inference about causal effects. And that's the ones Eric have talked about. It's multicollinearity, then it's this post-treatment bias, and it's collider bias. So I think that's the easy answer for this one. For the second one, think of one of these mechanisms in to each of these previous problems. Related to my own research, I have no idea, but these mechanisms and examples were also given by Eric, so I think we are fine with these as well. And what's the next question? Easy 3. List the 4 elemental confounds. Can you explain the conditional dependencies of each of them? So the 4s are fork, pipe, collider, and descendant. And fork and pipe both have the same thing. So X is independent of Y if we condition on Z. So if we know Z, X is not providing any additional information. That's true for fork and pipe. And in third, there is no dependency between X and Y, so they are independent. So there's nothing to do. And for the descendant one, it's tricky, but conditioning on the descendant on A would partially make it independent. But That's the last thing Eric has addressed. Yeah, and then I also did these in R, just with these dagities, similar as Richard McAgreth is doing it in his book. Just giving the same. We have like first a fork, second the pipe, collider, as well as the descendant. Yeah, and the fourth question I don't get. So how is a biased sample like conditioning on a collider? But conditioning on a collider then introduces a bias. So I didn't get the thing.
I think I might have an answer for this. So if we think back to the beginning of the book, like it says there, chapter, not book, we had that example of newsworthiness and trustworthiness of a study. However, as soon as and there's no relationship between the two, but as soon as we select only for those which got funded, so that is our bias. Our bias is we only look at funded studies. And as soon as we have that bias, because there's a trade-off between trustworthiness and newsworthiness in getting funded, you can either be super good in one and not so good at the other, or reverse, or somewhere in the middle on both and get funded. We then have the collider, because both of those feed into whether you get funded or not, and that introduces the relationship between the two.
Okay, yeah, I got it. And I also got like an example of it, like thinking of people you date. You either date like beautiful but dumb people, or clever but not so beautiful people.
We should have all been sociologists. We should have all been sociologists, seriously. Fantastic. You definitely get a medal for that example.
And I think that's it for the easy ones.
Julio. I can take over for the first medium one if you want me to, because that is the same as in the PDF version, but I don't have solutions to any of the other medium ones of the print version.
That's a pity. I like the medium 3, but you can take over, of course.
Oh, you can totally take medium 3. I would just take medium 1 if you want me to. Otherwise, just soldier on.
What is medium 1? Oh, it's to modify the DAG given on page 168. And like this part of the DAG is the part how it's given on page 168. So we have the effect from X on Y. Then we have these quite long path around it. I try to
just 1 second.
It, but
sorry,
yeah.
Sorry, just 1 second. For everyone who doesn't have the print version, or for everyone in the recording who doesn't have the print version, in the PDF, that is page 190. Just wanted to put that out there so it's on the record.
Sorry, I didn't know that these two
sorry.
different. Haven't looked at it.
Oh yeah, no. Sorry, go on. I just wanted to have it on record.
Yeah, sure. Yeah, and the question is like reanalyze the DAG. How many paths connect X to Y? So in the original one on 168, we have 3 paths. The first one, the second one, and the third one actually. And if we include these, I try to visualize it down here in this very ugly DAG. I will show you in a bit. But the answer would be we have 5 pathways open now, which must be closed. I think B is a collider. So we need only to close the upper path via A. And so that's how to condition on A to close it. And the DAG looks super ugly. I have no idea how you made these nice DAGs in the last lesson, like the one from you, Eric, as well as Gregor, but this DAG not really appealing to me, unfortunately. What is the next one? Yeah, that's just the answers.
So just to chime in for a second, if you want to make the DAGs look a bit nicer, you may want to pick up the ggdag package, in case you aren't using that yet. Thank you, Gregor, again for pointing that one out. That one I've been playing around with that way too much and procrastinating way too hard on my other work. And what you can do with that one is you can set coordinates of where each node should be exactly.
Ah, okay. Yeah, this would help.
Yeah, because otherwise it just sorts them probably according to some algorithm to maximize distance between all of the points, but that leads to really ugly overlaps in your edges.
Ah, cool. Is the code also provided online in one of your blogs?
Yes. So the code for, if you stop your screen share for a second, I will share my screen and I can show you how the DAG looks on my end. So there we go. So right here, I identify the different nodes, then I set the different coordinates for it. I build my actual DAG with the different pathways and tell it about the coordinates that we're interested in. I plug this all into a ggplot, and I get this kind of DAG, which is a very close approximation of what the book example looked like. It may still not be the most pretty, but at least we don't have the overlapping edges. So yeah, if you want to just pull that code off of my blog, feel free to just do it. I am also copy pasting code.
Yeah, and for the medium too, I think I failed and stopped in between. So
do you want to reshare your screen and tell us what medium 2 was?
yeah, but I failed midway anyway. So yeah, pretty long text. Sometimes in order to avoid multicollinearity, people inspect pairwise correlation among predictors before including them in a model. This is a bad procedure because what matters is the conditional association, not the association before the variables are included in the model. To highlight this, consider the DAG X on Z on Y, simulate data from this DAG so that the correlation between X and Z is very large, then include both in a model prediction. Do you observe any multicollinearity? Why or why not? What is different from the Lex example in the chapter? So I created first a DAG with this DAGity package where we have soil temperatures influencing soil moisture, and soil moisture is influencing above ground net primary productivity. So again, it's not as beautiful as it could be, but this would be the pipe we have from soil temperature to soil moisture and soil moisture to ANPP. And then I looked into this lag example in the code of the book earlier. So N is the number of samples, 100. I set a seed, random. I make like a random distribution of ANPP of soil temperature, and for soil moisture, I had no idea. So I just added 10 and multiply it by a smaller number to get like anything random, plus add some noise in the end. So that's how I tried to introduce this high collinearity between soil temperature and soil moisture. I make a data frame and I make a model where we have both of them in their soil temperature with this beta, soil moisture with this beta, all normal distributed, nothing super fancy or anything, and an exponential sigma. Yeah, it does something, but I have no idea about the interpretation of these outputs.
I think there's a bit of an oversight in how you simulated the data, because the way you simulate your data, even though your DAG implies that there's a causal relationship between soil moisture and ANPP, your simulated data doesn't show that. Because your ANPP in your simulated data is completely unrelated to soil M.
Just lost you for a sec, Eric.
Oh yeah, I lost you too. In your no, it's mine. It's always mine. I'm on a mobile hotspot. It's always mine. Um, so, so in your simulation, your ANPP, the values of ANPP aren't dependent on the values of soil M. So you cannot find an effect there.
So I just made like soil moisture depending on soil temperature, but not ANPP on one of those.
On soil moisture, exactly.
Yeah, yeah.
And I think what you will see when you fix that, you will see that your coefficient for soil M will be strongly not zero, and your coefficient for soil T will be broad covering zero. But if you then run a bivariate model with just ANPP and just soil temperature, you will find a strong non-zero effect for soil T. And that's the multicollinearity in that case.
Yeah, makes sense. Maybe I find the time to get this right, but I guess not, at least not over the weekend.
And you shouldn't. The weekend is for relaxing, and the weekend is holy.
Okay, so that's the fail of the medium 2 part. And I think medium 3 only works with seeing the DAGs.
Do you have them present?
I have the book, but not presented in there. So the questions about 4 DAGs, how should we?
In that case, if you were to go on share screen, you should be able to share a whiteboard. If you could draw them for us, that would be fantastic. And no pressure at all on straight lines, by the way, because I know how terrible it is to draw on this whiteboard with a mouse.
Yeah, it's a pain in the ass.
Mm-hmm.
Oh, Jesus.
It's definitely going to be more readable than if you just held up the book, though.
X, Z,
I hope they don't get too complex, boy.
Y. Arrow in this direction. Arrow in this direction. Yeah. Yeah, that's the first one.
And what are we supposed to do?
The question is, learning to analyze DAGs requires practice. For each of the 4 DAGs, so that's the first one, state which variables, if any, you must adjust for or condition on to estimate the causal effect on X and Y. So we are always interested on X influence on Y. And now I can't see my solution for it because of the whiteboard. Let me give a quick look.
This is also something that we could definitely pull in everyone else in the audience to see if everyone has an initial thought right away.
Is it sufficient to include set?
I think that's what I'd say too.
Yeah, because all that goes through A goes through set as well, so it should be sufficient to only use set.
Completely agree.
Yeah, and Z is a fork, so that's why I just close set.
Yeah.
Okay, the second one I will. Okay, in the second one, the entire thing stays the same. The only thing what's happening is that this arrow turns around. So we have in the second one, we have an arrow in this direction. So we have now a pipe here from X to Z to Y.
Wouldn't that just be the same?
I don't think we have to condition on anything here.
Oh, because nothing's feeding into X.
Yeah.
Ooh.
And also because we have that indirect effect that we're still interested in because we want the total effect, right? So X through Z to Y. If we were to include Z this time around, then we wouldn't be picking up on the effect of X on Y via the path X, Z, Y.
Yeah, that makes sense.
But then, shouldn't we condition on A? Because we have a path from Y to A to Z to X, and we have a collider in A. So
A is,
You mean
A is of
you
course,
mean a
the
fork?
collider is Z. So if we condition on Z, then we are opening the backdoor thing.
Exactly. Yeah. The path X, Z, A, Y is already closed because Z is a collider.
I see.
Yeah. So there's nothing to condition on in this one.
Nice job, Eric. I saw that.
I was no. When Greg has said that, I went, oh shit, did I misspeak? No. All right.
The last two are again some drawing action. So we have again X, Y, A, Z. Let me have a look. This goes like this. This goes like this. Yeah, that's the third one. Any quick solutions?
Isn't that the exact same thing? Just now A is on the left side instead of the right-hand side. So we shouldn't condition on anything again because Z is still a collider.
Yeah, I was confused. Why is Z a collider?
Because Z gets both X and A input. I really think this is the exact same thing. We don't have to condition on anything. So what we do want to have is the path X to Y, and we also want to have X, Z, Y. So we don't want to touch these paths. So the only backdoor that we have to look at would be X, A, Z, Y. But X, A, Z, Y is already closed because there's a connection between X and Z, thus making it into a collider.
Yeah, true story. That's, by the way, the same I found out yesterday evening. No idea why I'm now confused about it.
You probably had more coffee in your system.
Oh. Wait, no, we must condition on a thing here. It's actually, it's not the same. Wait,
Oh wait, no, yeah, no, true. Yeah, sorry.
Condition on A.
Because the arrow that goes out of Z makes Y a descendant of Z.
Yeah, we need to condition on A in this example.
Yeah, no, you're right. Yeah.
Okay.
Yeah, no, if the arrow between Z, if the arrow between Z and Y were flipped, then we wouldn't have to condition on anything.
Yeah, and that's actually the last example.
Right.
Where we just flop this arrow around. Discussed this already in detail. Nice.
Cool. All right, should I take over for H1 and 2 then? Let me, over here, my solutions, share the screen. Very well solved, by the way, Bernd. Thank you very much for stepping in with that. Medium exercises we just talked about, so now we're going into hard exercises. I only had an H1 and an H2. I guess the book has more, but I hope that for the sake of today, H1 and H2 will suffice, so that we all get our Bayesian fix for the weekend and then we can chill a bit. So hard exercises, practice H1. The question here is to use the Waffle House data that is contained within data waffle divorce, which, by the way, great name for a data set. And we now are tasked with finding the total causal influence of number of waffle houses on divorce rate. We should justify our model with a causal graph. So what I do first is I start by recreating the DAG that in the PDF version of the book is on page 191 with the code that is on page 192. And I spruce it up with some coordinates so that I get this kind of output. So what I have here is that southerly position of a state drives marriage rate, also drives, in this case, age of people, which probably a nonsense link, but the DAG wanted me to have it in there, at least the book one. Age drives marriage rate drives divorce. Waffle houses are caused by a southerly position. Waffle houses may cause divorce, and age also may cause divorce. So now I wanted to check which variables I need to condition on to allow the full causal identification between W and D. So waffle houses and divorce rates, because that's what I wanted to identify. Is there a causal relationship? So then I just run the adjustment sets function on my DAG object. Exposure is W, outcome is D. And I need to either condition on A and M, or I need to condition on S. So I chose to condition on S because that's less variables I need to worry about. So what I do is I load the data set, I duplicate the data set so I don't change stuff on the original one. Then I scale the divorce, scale the waffle houses, and scale the southerly positions just so I can set some priors more intuitively. Then I specify my model where I specify D, divorce, to be randomly distributed with a mu and a sigma, mu being a linear combination of southerly position and W being waffle houses, sorry. Setting a prior for my alpha, setting priors jointly for both of my predictors here, which I think is great that we can do it like this. And I wish the book would have told us about this earlier, because I really think that this is much more elegant if I want to assign the same prior to multiple predictors. And then I obtain my output. And what I can see is that having accounted for the southerly position, suddenly waffle houses don't have an unambiguous effect on divorce rate anymore, but southerly position does. So my finding being that once I know where state is located, knowing how many waffle houses are in an area doesn't give me any more significant, sorry, not significant, but meaningful information about divorce rate. Trying to ban significant from my language there. And yes, language policing is very real in this study group. All right, practice H2. Question being to build a series of models to test whether the implied conditional independencies of the causal graph I used in the previous problem, so from page 191 in the PDF book, to test for these implied conditional independencies in that graph. If any of the tests fail, how do you think the graph needs to be amended? Does the graph need more or fewer errors? Feel free to nominate variables that aren't in the data. So I look at implied conditional independencies. So A should be independent of W if I account for S. D should be conditionally independent of S given A, M, and W, and M should be conditionally independent of W given S. Not going to go too much into the DAG and reading that out ourselves because we've just done that for a few exercises and we can just run it with R, so why don't we just do that? So first, again, I load the data set because I want to have each of these solutions be able to run by themselves. I scale all of my variables which are relevant again. I then look at the different implied independencies. First one being A independent of W when given S. So I plug S and W into my model. I look at the output and I see that the effect of W is not meaningfully non-zero, which is a double negative way of saying they are conditionally independent. Next model, I look at A. This is still the answer to this one because I've confirmed the independency. Next one, I look at D as a product of S given H, W, and M. I plug all of these into my model, assign the same prior to all of these, run my actual model. And again, I find I'm interested in SBS to overlap with 0. Now, there is still quite a bias towards the right-hand side, but because it had gotten late yesterday when I was solving these, I did not care about this whatsoever. I just saw that this doesn't seem to be meaningfully different from 0, so I'm just going to go on. Now I look at marriage rates and whether that is conditionally independent of waffle houses given S. I have already tested this in the previous exercise because that is what I did there. So when I run this model, I see that BW overlaps because I've got both of these in here. And again, I have this confirmed. I finish this off by just extracting the posterior for the relevant parameter from my model for each model, so that I can just plot them here with this really cool stat half-I function from the tidy base package, which gives me the distribution as well as these interval points here with the median in there. And I can see that all of these are very, I'm very uncertain of these parameter estimates, and they don't seem to be very meaningful. So I would actually say that I have proven all of the conditional independencies in here, and I do not need to amend the graph in any way. I also have to say that I have not checked any of this against the solutions manual that I found half an hour before we got together today. I just assume that this is right. And that was my solution to H1 and H2.
That looks really cool. That start half-I function, I'm definitely going to steal that.
You should.
That looks really good.
Mm-hmm. I was pretty excited when I found that. All right, cool. And with that, we are actually at the end of our session today. Recording will go up probably tomorrow because I still need to upload a bunch of data sets I've been producing over the last few days, and my mobile hotspot isn't that fast. And I'm really looking forward to seeing all of you next week. Don't forget, the week thereafter, we're having our first input talk. For everyone who wasn't here earlier, all of the input talk slots have been filled now, and I will send around an update email on that with the updated schedule later today. Thanks for showing up. Thanks for being here. Thanks for the input.
Thanks, Eric.
Yeah, thank you.
Enjoy your weekend.
Cheers, Eric.
Bye.
Cheers. Bye.